Hello everyone, welcome to another short video on solving a LeetCode problem with APL. Today we will be solving problem 136 after someone requested it on the comments and I thought, well, why not? So yeah, let's tackle this problem. Now this problem has a very specific statement because it describes a simple task, but then it tells us the runtime complexity that our code should have and also the space complexity of our algorithm yeah. So yeah, what it says is, given a non-empty array of integers, every element appears twice except for one element, and we need to find that one. And then it says that the solution should have a linear runtime complexity and can only use constant extra space. And then it gives us a couple of examples. So over here the 2's show up twice and the 1 only shows up once, so the output is 1. Over here it's the 4 that's unique, so we have the 4 over there, and in here the 1 shows up alone, so that's the 1. Now cooking up a solution for this in APL is not very difficult actually, so let's see. Where's my interpreter? It's over here, so let's type in my input vector. Now I think it's fairly recent, but APL now has a unique mask primitive, and that's the not equals. When it's used monadically, you can get a boolean vector that's telling me where the unique elements show up. And so what the zeros here tell me is that the 1 and the 2 are repeated. Now what I can do is, if I negate it, I can get a boolean mask for the repeated values. And now what I can do is I can take the original, I can take this boolean mask and compress the original vector so that I keep only the repeated ones, right? Now what I want is the element that's not repeated. So what I can do is I can say, well, can we please take the original vector and remove all the repeated elements, and now I get the 4. So this is a let's say a fairly straightforward solution in APL that I could write as omega without the reduction of the negation of the unique ones. So this is my solution as a diffn. So let me say that this is the solution. Okay. Now the thing is, this isn't necessarily linear. To be honest, I'm not entirely sure of what's the complexity that the runtime complexity of without, which is the primitive that we are using there to remove the duplicates. But there's another clever algorithm, except that it also doesn't fall within the specification of the extra space that we are allowed to use, because there's a really clever solution that takes the numbers and then just does some bitwise operations on them. And it uses the XOR, which is the exclusive OR, the Boolean function. And what that Boolean function does is it's going to go through all of the bits, and then every time, so for each bit of a repeated number, the original number and the repetition, the bits will cancel out. So in the end, only the bits of the element that is unique will survive. Now the thing is, APL doesn't have a Boolean XOR. So what we need to do is we need to convert to binary by ourselves. So we need to do the conversion, and then we need to use not equals as the exclusive OR. So we need to do a reduction to apply the not equals through all of the rows, which represent the different significance levels. So this is 2 to the power of 2, this is 2 to the power of 1, and this is 2 to the power of 0. And then when we use the exclusive OR through all of the rows, what we can see is that the repeated bits will cancel out, and then only the binary expansion of the unique digit remains, which is in this case is 4, and then we need to do the conversion from binary again, or by hand. Now the problem is this conversion right here, this is going to take, it doesn't take constant space, it takes linear space, because this matrix here grows with the size of V. So if V were much larger, for example, if V had thrice the size, then this matrix would have thrice the size. So this is also linear in space. But the thing is, the solution that the problem had in mind was using this bitwise XOR, and APL doesn't have it. So from the limited time I spent thinking about this problem, this was the best I could come up with. This that tries to emulate this one that tries to emulate the clever solution on other traditional languages, and then also this one that we saw here, that's quite clean. But yeah, I'd be really interested to know if anyone can come up with a solution that really has. Well, to be fair, I was thinking while I was talking. So to be fair, we could actually make sure that this has a constant space if we do the conversion by hand as we go. So if we do the conversion as we go through the array, we can make sure that we never spend more than a constant number of bits. So we don't occupy too much space, because we know that we are always only converting 2 numbers at a time, and those 2 numbers, well, they are limited in size. So where is it? We have the restrictions here, so the numbers are limited in size, so we know that there's a fixed number of bits that they take up maximum, and so we can do this in constant space. So let's see if I can come up with a solution on the fly. So being wasteful, so this is a little bit wasteful, but we could do something like this, which is just take what's in here. So we can copy this as if it were the full solution, but then what we do is we apply it to alpha and omega, so the 2 elements of the reduction. Yeah, and then in the end, the unique element is what comes out. I'm sorry if I'm just babbling too much, I just thought of this. So what's happening is we are doing a reduction, so think of it as going through the vector, and then we take the 2 numbers, we put them together, then we convert them to binary. Now this takes constant space, because it's only 2 numbers, and we know that they have a limited number of bits. Then we do the exclusive OR of the 2, and then we convert back to decimal. And this is a little bit wasteful, but it works. So now if I do it thrice, I can also get the 4 back. Now I can do something like 1, 2, 3, 4, 5, 1, 2, 3, 4, and I get the 5 back. So this is a possible solution that's linear, and takes up constant space. Cool. Now if you have other solutions, please do leave them in the comments below, because I'd be really interested to take a look at them. Yeah. And otherwise, I guess I'll see you in the next video. Bye.